Okay, thanks a lot. Thanks to the organizers for giving me the opportunity to speak. Thanks. I will talk about functors between categories, and these are inspired by a physical setting called the gauge linear sigma model with a Abelian gauge group. Okay, let me first talk about very briefly about defects in two-dimensional TQFT. So this is a picture that can be looked at by mathematicians as well as physicists, and mathematicians might look at this in terms of some categorical framework in a symmetric monoidal two category where you have objects labeled V and U and one morphisms X and Z and two morphisms. And then there are such identities in a nice mathematically well-defined setting. This picture should also speak to physicists who maybe even want to read this picture outside topological quantum field theory, but also other quantum field theories that may, for example, not be topological. For me, they will mostly be topological, but I would like to have some comments on non-topological theories. And here you're supposed to interpret the labels U and V as labels for bulk theories. So they specify like some quantum field theory, and these things X and Z are defects between field theories. So they can, for example, be given in terms of some action or something where you have extra defect degrees of freedom that may couple to these bulk degrees of freedom. And then you have these local operators, and you may take their OPE, and you may also consider merging the defects. So in a topological context or in a math context, merging the defect is just kind of like composing the one morphisms in a category, and it's a well-defined operation. In physics, it may not be, it may be very, very singular if this is a non-topological theory, for example. Anyway, I would like to talk about this merging of defects in a mostly topological context. There are some special cases that will play a special role also in my talk. So one special case is that one of these theories may be empty. So for example, this one. And then the defect here becomes a boundary. So it's a morphism between a theory and a trivial theory. And the other special case is that all of these theories are the same, and the blue lines are just identities. So there's an invisible defect that just does nothing in physics and poses trivial gluing conditions, and in math it would be the identity morphism. Okay, so I emphasized that there are these special cases of boundary conditions and that are part of the category, and oops, some of the colors are not, that's bad, are not visible in this projection. Okay, unfortunately, part of my pictures also in the following will be white, although they are light or blue on my slides. Okay, so wherever there's a label, there's also supposed to be some part of the theory, not necessarily empty. So what I depicted here is kind of a functor between categories of boundary conditions. So I have this boundary condition B, and there may be the objects in the category I want to look at have as objects boundary conditions, and as morphisms boundary changing operators. So, and now I would like to think of a boundary condition in a theory B and map it to a boundary condition in a theory U, and I have a defect between B and U. And now I get a boundary condition in U by just moving this defect over to that boundary condition. And that is the composition of one morphism if everything is nice and well defined, and a mess if it's a physical theory. If everything is topological, then this operation is sort of a functor between categories of boundary conditions. I also refer to them as D-branes because that's the application I'm mainly thinking of, but it has no specific meaning or relevance in this context, call them branes or boundary condition. It's not necessarily a string theory context. Okay, so here's the specific context I'm thinking of. So I'm thinking about two-dimensional theories, one-dimensional line defects connecting two different theories. And often in physics as well as mathematics, we are in a situation where we don't have just single individual theories, but families of theories that may be connected, that may be part of some moduli space, connected by, in physics terms, by marginal deformations, or there could also be connected by relevant flows going beyond moduli spaces. And then defects can be used to connect theories at different points in a moduli space. So let's say we have some moduli space and P and Q are points in that moduli space, and to P and to Q we have associated some theories that live at those points. And now we can think about how to connect the theories P and Q by a defect. And one way to think about it is to first start with an invisible defect drawn here in dashed lines. So that's the identity on the theory at the point P. And then we consider perturbing this part, so everything left of this defect by some marginal deformation. If it's a moduli space, we take some path, so there's some direction in which we perturb. And then this theory will be deformed to a deformed theory T of Q. And then a defect builds up that connects theories at points P and Q. So the defect labeled R here connects theories at different points in moduli space, and it will depend on how we perturb. So in particular on a path in moduli space. As I said, we can think more generally, more beyond moduli spaces, namely relevant perturbations. Namely relevant perturbations. So that means a flow defect. So it's, I call it flow if it's a proper flow between a UV and an IR theory. It will connect two theories related by a relevant RG flow. This kind of setting has been looked at in various contexts starting in 2007 and later. So in a topological context, in the case of simple sigma models with easy targets and then full CFT, and in the case of conformal minimal models, also full CFT and non-topological flows, non-topological setting and RV flows. Yes.
How does one know in the different theories what is the appropriate data for a defect? Is this from abstract considerations or how?
What is the appropriate, so in a different theory, what is the appropriate defect? Well, it depends on what the theory is. So for example, in conformal field theories, you have good ideas how to construct them, in particular rational conformal field theories. So for example, Christoph knows everything about how to do that. And then in topological theories, I will name some examples where you also know how to do the defects. And in in many other theories, you can, yeah, for example, you can think of this picture as folding this, and then you can, if you know how to think about boundary conditions and D-branes, then this identity defect is some diagonal thing in a theory times its copy, and then you can perturb it. So when you know how to do perturbation theory, you know how this thing behaves when you perturb and flow. Yeah, does it answer your question?
Yes.
Yes.
When you say this moduli space, what should I have in mind? Like, what's an example? So, like, what kind of moduli space you're doing?
Yeah, I will give some examples in a moment, and you can maybe tell me then if you are happy with it or not.
But it means it is the moduli space of theories, or is it moduli space parameterizing some parameters of single theory?
It could be, yeah, I would like to think as general as possible. Simple examples are like, I don't know, geometric examples where you have like, I don't know, a circle and there's a radius that parameterize a family of theories on that circle. And then you can think about changing that radius. But I would like, yeah, in a certain way, I would like that you also think about different theories and that they may be connected by such thing, and that I will say how that may go in this setting, of course.
Thanks.
Are there more?
Here, there's a question.
Yeah.
Your picture is kind of obvious that the path connecting P and Q became a defect. But however, I don't know whether every defect can be viewed as a path. Do you have any comment there?
Right. So what I would like to advertise is to say that what you expect. So if you think that such defects exist, what properties they should have, and then you expect kind of that between given 2 points, you have like more than one defect connecting the 2 points, because you expect that there are different paths. And therefore you expect that your construction of defects should give rise to a non-unique result. And then you hope that you can match your path with your defect construction. Does it answer the question?
Yeah, but whether it is possible, there are certain defects do not correspond to a path.
So we learned about the twist defect yesterday. That would be also an option.
The twist we had yesterday. What twist we had yesterday? Yeah. I don't know. So I'm having something in mind, like in the simplest case, that you have some moduli space, and for example, some singular point or something, and then your path, your defect depends on how exactly you pass this singular point or something like this. Does it make sense?
Okay, yeah, maybe we can go on.
Okay, so let me continue. So here's the thing I said in words now before. So let me first emphasize, so if we have physical theories, so in particular non-topological theories, such as, for example, conformal field theories, then the defects I'm talking about are not topological. So in particular, if there's a relevant flow or something, then the central charges on the two sides of the defects will be different. So they're not topological, and therefore these fusion or composing the defects is highly singular. And therefore, I would like to be in a sort of favorable situation, quote unquote, where I can extract some subsector that one can handle. So for example, one may look at supersymmetric theories and topological subsectors. In simple examples, this fusion is possible to work out explicitly, such as like free field examples and so on. Then one can compute this and subtract singular terms. Okay, so let's think what the properties of the defect should be. So I'm again drawing a little diagrams here. So again, on my slides, there is a colored IR region as well. So here we have a piece of space-time on which my theory is defined, and I imagine that I perturb the theory in certain regions of that space-time only, and I leave open a piece of unperturbed region. And then you may imagine to kind of make this unperturbed region smaller and smaller. That amounts to kind of letting the two lines labeled R and T approach each other. And then in the end, you would have perturbed your theory everywhere. And you would expect that this is just the IR theory. So you expect that the composition of the defect labeled R with the defect labeled T yields the identity on the IR theory. Then as a consequence, you get a projector in the other direction. So if you have the UV at the outside, you squeeze in a little piece of IR and you merge the two lines, however difficult it may be or however easy it may be, you get a projector on this theory UV that kind of remembers that the IR theory was squeezed in. Right. I on purpose didn't, so this is kind of some semi-invertibility condition. On purpose, I didn't give these lines any specific orientation or call the defect adjoints or so, because that leads to stronger restrictions than I would want. In particular, I would like to remind you that there may be a difference between left and right adjoints of any defects, and yeah, as a consequence, this picture would then not be unique, and the kind of algebraic properties that the defects T and R have are general. So in particular, I don't know, the setting might remind you of orbifold. So let me try to draw something. Draw something. Where's the pen? It's here. Right, I can draw something. So let's think about a piece of worldsheet, and you kind of like want to start perturbing things. So these shaded regions are now supposed to be the perturbed regions. This is E, and these shaded things are IR. And then you may think to just by and by perturb the whole theory, and in that way get IR everywhere. And you may then think about these defects P as kind of, double lines. No, I don't know how to get out of this. Double lines like this, and think about properties of such double lines where you squeeze in one of the theories, and then the properties of these lines labeled that I call P here are different than the lines you use for orbifolding, although this picture looks fairly similar. Okay, so that's what one would expect. Okay. Yes. Okay. So now let me go back. Now this thing is no, it's more complicated than that. I erase this. Okay. So let me go back to this picture. I would like to now think about the situation where this theory B is a theory at a point in moduli space, and I would like to think about how to map boundary conditions from one theory to another in a moduli space or along a relevant flow. using the properties of the flow defects that I advertised. So here are some examples. So where does it work and in what situations? Well, it works for topological subsectors of supersymmetric theories, for example. And here an important condition is that the perturbation and boundary condition preserves the same supersymmetry, otherwise there will be no compatibility with the topological twist. So here are some examples. So for example, D-type branes on Calabi-Yau manifolds together with Kähler moduli. You might object that, okay, let's say what this is. So from a kind of small volume perspective, one would relate these branes to orbifold or Landau-Ginzburg branes, or the theory to orbifold or Landau-Ginzburg orbifold points. And the relevant category to look at would be a category of matrix factorizations or equivariant matrix factorizations. Then on the other hand, you may want to look at this category through the perspective of geometry, more appropriate at a large volume perspective. And then you would relate it to a bounded derived category of coherent sheaves. And now what do we want to do? Well, we want to have functors between different brane categories or between brane categories. So for example, between that category and the Landau-Ginzburg orbifold category. And indeed, one expects that there's more than one functor and one functor per homotopy class of paths. Okay, so that's one class of examples I want to look at. And the other is sort of related. So it's Landau-Ginzburg models. So those are theories of chiral superfields specified by a superpotential W. So W is an element in a polynomial ring, and it describes some isolated singularity. One can associate TQFT with a state space that looks like this. An example I want to look at is just one variable case, W is x to the D. And then I would like to look at relevant flows. So this example was something where we have a moduli space, so Kähler moduli space with non-contractible paths in them. And here's an example where we have flows between theories specified by different powers of these variables. So from monomial x to the D, we can flow to some lower monomial x to the A is strictly smaller than D. And then there's a category of boundary conditions in here that is given by matrix factorizations. Okay. And now the point is that all of these categories I described can be viewed from the perspective of a gauge linear sigma model that's kind of known since '93, where Witten wrote his paper on gauge linear sigma models. And their phases, so these are n equals 2,2 supersymmetric gauge theories and depend on some parameters called complexified Falley-Oliopoulos parameters. There is a mathematical language in terms of toric varieties and hypersurface and toric varieties. From a physics perspective, the theories are specified by a gauge group. In my case, it's an abelian gauge group U1 of some rank K. Then there are chiral meta fields. So that means a representation of this gauge group specified by some charges or weights under this U1. There's a superpotential, so it's a function and it's G invariant. There may be some R symmetry preserved, for example, U1 or also subgroups, and the charge assignment is such that W has weight 2. Then there's a potential for scalar fields, and they fix a classical vacuum manifold. And then there's a condition that this potential vanishes, and regions where the potential vanishes may look different in nature. So for example, there can be geometric phases or Landau-Ginzburg phases. So the things I showed on the previous slide arise as different phases in this setting. Here's an example. So for example, the group may be U1. That implies that we look at the situation with a single Kähler modulus. There may be 5 fields and one other field of a different nature. The 5 fields have charge 1, the last field has charge -5, and then we can look at the homogeneous polynomial of this form. So W is supposed to be of degree 5, and then altogether this has degree 0. And we can also assign U1R charges, and this model exhibits different phases. For example, geometric phase specified by the vanishing locus of this part of the potential, interpreted as a hypersurface and projective space. In this phase, the gauge symmetry is completely broken. Then there are also Landau-Ginzburg orbifold phases. They are specified by the superpotential, and there's an unbroken gauge symmetry Z5. Let me present a different example, namely an example with 3 different Landau-Ginzburg orbifold phases and no geometric phase. It has gauge group U1 squared. It has 2 parameters, 3 chiral fields. This is the homogeneous superpotential. The charges of the fields are summarized in this table. Now there are 3 Landau-Ginzburg orbifold phases. Basically 2 out of 3 fields get an expectation value in each of these phases. So there's a phase x0 to the d divided by zd, and then for each one of them x1 to the d minus 1, and so on. And between these Landau-Ginzburg models, one has relevant flows that we want to relate to defects, or that we want to construct using defects. So this is a so-called non-Calabi-Yau model with a running coupling constant. So it means that we expect that in the brane category, some part of the branes or of the boundary conditions will be lost along the flow and projected out. So in the context of gauge linear sigma model, this was considered in this paper. And if these people described how to still embed different phases in one gauge linear sigma model, though the coupling is driven from physics perspective to a particular value, so that there's one IR phase in the end. Okay. So these models are related by mirror symmetry to non-orbifolded Landau-Ginzburg models, and therefore also to singularity theory. Okay, at the beginning there were sort of many questions. Now there are no questions. Other questions, or should I say anything else?
It's not clear to me any of these models what are the moduli spaces you referred to at the beginning.
So these models don't have moduli spaces, so they are related by a relevant flow, and we look at defects that build up as a consequence of the relevant flow, and I can later tell you, so I will later tell you how exactly in this example, how the defect data maps to data that you may expect from the mirror perspective. So the mirror perspective in this case is rather geometrical, and you may have a geometrical idea of what the branes do. Other questions? Okay, so I picked here something like, there's something in the chat. Does anyone control the chat, or should I do this?
I will do.
Okay, good. Then, okay, oops. Let me say that this is part of a bigger story, of course, so you can kind of flow all the way down and make this so to smaller and smaller powers of the superpotential. And you can also make the relation to singularity theory more concrete. So this is just for people who may be interested in this. So you can think about orbifold singularities. So this simple orbifold C2 mod Cn has a nice, and its resolution has a nice toric description. So in the field series setting, it means that we look at the gauge linear sigma model with these fields and those charges and no superpotential. And then this model exhibits an orbifold phase that looks like this, and it exhibits a resolved phase where the singularity is resolved by a chain of U1s. And now the model I presented looks like this. So it's almost the same assignments. So this part of the table looks like before. And the model I presented before was anomalous. So in particular, it really restricts to the singularity and leaves alone everything that is not coming from singularity. And the only difference in this table is one added line, which yields, which makes all the difference and lets us isolate the singularity from the rest of the geometry. So this model captures the physics of the singularity as opposed to all the physics of C2 mod Cn. Okay, so now what do we want to do? Well, we want to look at branes and phases of gauge linear sigma model. So there are different phases, for example, Landau-Ginzburg orbifold phases and geometrical phases, and they arise as different limits from one bigger theory that I called gauge linear sigma model. And so what are our defects supposed to do? Well, they're supposed to lift phases from, lift boundary conditions from a given phase to the theory using a defect T, and also let us go down again from the GLSM using another defect R. And then this holds this you can do for all the phases, and you can compose the defects and map boundary conditions from one phase to another, taking this detour via the GLSM. And in this way, for example, get defects or get functors that relate the category of coherent sheaves to the Landau-Ginzburg category. Okay. Good. So what do we do? Well, we consider this gauge linear sigma model. We do a B-twist, go to the topological sector, in any case, decouple any dynamical gauge degree of freedom, and put us hence in a setting where we have an explicit description of the brane categories. So in the geometric phase, it's this category. In the Landau-Ginzburg phase, it's a category of matrix factorization with some equivariance conditions. I replace the gauge linear sigma model by a U1 to the K equivariant Landau-Ginzburg model and take the branes from there. So then that's good. We know all the defects in those categories, and now we can manipulate them to construct defects between the phases. So all that we need is basically the form of the invisible or identity defects. That's why I made some noise about it at the beginning. And then from it, we want to obtain the defects between the phases. So here's now the pictures that I showed before. It's now relating phases to GLSMs, so phases to gauge linear sigma model. So we want to find for each phase a defect that lifts the phase to the gauge linear sigma model, and that also semi-inverts this. So we want to find these defects T and R for each phase, such that they fuse to the identity, and therefore we get the projectors in the other direction. And this projector realizes the brane category in the GLSM. So I lift the phases to the GLSM and they are lifted to some image that in the set of GLSM branes that is specified as the image of some projector that we construct. Okay. So I want to construct everything from the identity defect of the phase and also of the gauge linear sigma model. So here's a mock picture how to do it. So let's start with the identity defect of a phase. I'm imagining it's, for example, a Landau-Ginzburg phase, where some of the fields that were there in the initial gauge linear sigma model obtain some expectation values. So in the phase, we have fewer fields than in the gauge linear sigma model. And now I want to lift this phase identity to something that has one leg in the gauge linear sigma model. So I'm again putting this example here that I had before. So let's start with the theory that has 3 Landau-Ginzburg phases. So there's, for example, the phase x0 to the d connected to, with the identity defect to itself. So this is to a copy of itself. And now we want to lift this to the gauge linear sigma model. So that means we somehow need to include the other 2 fields and to kind of make this take into account also the gauge symmetry. So there's a discrete gauge symmetry here, ZD, and this thing has U1 squared gauge symmetry. There are a priori many ways to do such things. And we want to pick those that we can interpret as coming from a gauge linear sigma model. So start with the identity on the level of the gauge linear sigma model, set things to their expectation value on the right-hand side, and then see what one gets. So just putting things to an expectation value isn't enough. One needs to truncate things, and in this way single out a class of the defects that one obtains from this perspective. So that's the kind of strategy. And I think the next slide is about identity defects in the categories that we are looking at. Are there any questions? Okay, so this is the strategy, and now we are in a setting where we know what this is, we know what this is, and then we have to see how to get these things. Okay, so there's some explicit construction. I will just say a little bit about this. So the main players are just identity defects and phases and gauge linear sigma model, and we can write them down. We regard the gauge linear sigma model as a G-equivariant Landau-Ginzburg model. And then let's look, for example, at Landau-Ginzburg orbifold phases. There we just break this G to some discrete subgroup and eliminate some of the fields. So we just need to talk about defects or identity defects in different Landau-Ginzburg models with different equivariance groups. And then we know that such defects are one morphisms in the category of matrix factorizations. And the matrix factorizations factorize the difference of the Landau-Ginzburg potential. So we have polynomial rings that refer to 2 sets of fields on the 2 sides of the defects. I denoted them here as X and X prime, referring to the different sides of the defects. And then there's a superpotential on each side of the defect. And now we look at a pair of modules for this ring, P0 and P1. And this is a Z2 graded situation. And we look at maps P0 and P1 that compose to the identity on P0 if you compose them in this direction, and likewise P0 times P1 as the identity on the other side. So that specifies matrix factorizations. And for example, we now need to think about the identity defect, and for a single variable, it just looks like gluing X to its primed partner. And that means that we want to consider P1 equals x minus x prime, and then P0 is just W1 minus W2 divided by this thing. Okay, then one can associate to a matrix factorization the co-kernel of this map and recover the matrix factorization from it because this thing is has a two-periodic resolution, or a resolution that turns two-periodic after finitely many steps. And so we may think of the identity defect just as some ring S divided by x minus x prime, and this S is the ring of the fields divided by differential, or by the difference of the superpotential. Okay, then people know how to compose one morphism, so this works like always, or like in similar situations. So you have two matrix factorizations and want to compose them. This is again drawn in this picture. So three theories characterized by superpotentials, W1, W3, 2, W3. And if you compose them, it amounts to taking a relative tensor product of matrix factorizations in this case. Okay. So now we want to make things equivariant, and it means that we have to specify group actions on the modules P0 and P1, and everything has to be compatible with the maps. And we do that, so if you look at the identity defect, then this thing, so x minus x prime, is not equivariant under a group that acts differently on the two copies of the variables. So we need to do something, and what we do is to take tensor product with the regular representation of the groups that we want to look at. So for example, for U1, the regular representation can be written in terms of extra variables. So in physics, I would say I include extra defect degrees of freedom to make things equivariant. And so let's just include this in the matrix factorization. And then we can write an identity defect of the gauge linear sigma model. So here the point is, before I had kind of one version of fields, so x1 minus x2, it's not equivariant. And now I have these alpha variables and they carry some charge. And in this way, I have made this identity defect something equivariant. Okay, so that's the identity of the gauge linear sigma model. And to get the identity in a phase from it, I can simply set things to their expectation value. So if I go to a phase, then on both sides, fields get an expectation value, and then that would impose relations on these group variables. And in particular, gives us the phase identity from the GLSM identity. Okay, so that's not the thing I wanted to do. So what was the thing I wanted to do? In the end, so we now saw that we get these identities, invisible defects from those invisible defects, so they are closely related, but the thing we want to do is something in between. So we want to have a consistent defect between this GLSM and the phase based on this identity. Okay, great. So if we start from the phase identity, then the symmetry is broken to a discrete subgroup of G. And there are many different ways to promote to a G equivariant case. And all of these possibilities will be finite dimensional in nature. If I start from the gauge linear sigma model identity and set fields to their expectation values on one side, not on both sides, then this will yield an infinite matrix factorization. And to make this compatible with the idea of lifting the phase, we need to make it finite somehow. And what we propose is to impose some finiteness condition. In the single U1 case, it means to just specify a maximal weight for alpha, so some maximal power that this alpha field can appear with. Just putting one limit makes it finite, in fact, because the relations are designed to do that. And then one can generalize this to several U1s in a more or less straightforward way. And then what we observe is that each choice of truncation yields a consistent lift from a Landau-Ginzburg phase to a gauge linear sigma model. And in this way, one also obtains defects between different Landau-Ginzburg phases by setting fields to appropriate expectation values. Okay. Let's talk about defects between Landau-Ginzburg phases and geometrical phases. So we are looking for a functor between the category of matrix factorizations and the category of coherent sheaves. What we have is right now at this point is a defect that is a matrix factorization that looks like this. So it relates the Landau-Ginzburg model to a geometric model. So that means we have a matrix factorization of the difference of these potentials that can be written like this. And now we still need to push this leg somehow to the geometric phase. And we do that by a sort of version of Knörrer periodicity. And we obtain some object that is an intermediate object between matrix factorization and some Fourier-Mukai kernel type of thing in the category of in the derived category of coherent sheaves. And what we do is to I don't want to do it here because it would be rather technical, but the idea is to integrate out, quote unquote, this field to P, or more concretely, I wrote in small some first steps here. So we have two modules here, T1 and T0, and P is part of these things, and we kind of pull out P, and P has some R charge, and therefore we count. So the R charge, so we need something, so we started with something Z2 graded, and we need something Z graded to make it good for the other category, and this P has the role to assign proper positions in a complex, so the integer positions and not Z2 positions. Yes.
Some like construction that would come out of some category considerations, or is this something one has to do by hand?
You mean so to get the concrete thing, you have to, I think, do this by hand. I mean, it looks a bit bad here, but it's conceptually it's not so hard. That's what's happening. So you kind of just want to use this P field to get something geometrical on the other side, and then these arrows kind of decompose into stuff that will give rise to matrix factorization kind of stuff, and stuff that squares to zero, and that and then that you have to do. And as I said, it looks like a kind of version of a Knörrer periodicity. So Knörrer periodicity would relate some things with superpotential W, the Landau-Ginzburg category, to the one with W plus UV, and UV are two variables. And now we have P times G would play the role of U and V. And so you could probably more conceptually think about it like in those terms.
Okay, so I meant more, is it like some categorical concept of integrating out, like maybe just that you're taking some coend or something like that, or is this not?
This I don't know. I would think that it's like, I don't know. So in Faulkner periodicity, you can think about like taking a tensor product with a certain matrix factorization, and then that's kind of like some obvious way in a functor gives you a functor, and this something like this should work here, but I don't know about any proper terms or anything for this here. So it's kind of clear what to do and how to proceed. And then you can also, you can also still apply this to the branes and move them from Landau-Ginzburg to large volume, for example, because I don't know, it's some nested cone construction. Maybe this will give a hint what it might be. And this commutes with taking tensor products with the branes, and therefore it's nice. It's still a nice operation. Okay. Right. So let me stop with the geometric example. So we have this functor from matrix, so from the Landau-Ginzburg category to the geometric category. And here is, I think, the simplest example that is still moderately interesting that we can discuss in some more detail. So it's a situation where we have several Landau-Ginzburg phases, and our defects are supposed to connect different Landau-Ginzburg phases. And the nice thing is here that we have some mirror description of the situation. So our phases of the GLSM are related by mirror symmetry to non-orbifolded Landau-Ginzburg models, and in this way there's a geometric picture about what the branes are. So they are described, so A branes are Lagrangian submanifolds. So here we have one variable, so they are straight lines in C, and they are not any straight lines. There's a reality condition coming from the superpotential. So here's a picture for W equals X to the 8, I think, yes. So there are kind of these lines that I drew that map, that become real if you map them with the superpotential. And there's an obvious Z8 symmetry in this picture by rotating this disk. And then the branes are specified by pairs of such lines. So for example, this would be a brane in the category, or this green thing would be a brane in the category. And now, if you perturb this model, then what happens is, so let's go to some lower potential, then it just means that one of these wedges has to collapse and the corresponding brane will decouple. And in this way, we have a nice geometrical picture about all the RG flows. So what are the possible paths that can be taken? So someone was asking how I know that the defects parameterize the path. And so in this example, one can give a direct map to it. So each flow is determined by saying like which of these wedges will decouple from the flow, will decouple and and vanish and in the image of the RG flow. And now under mirror symmetry, these elementary branes get mapped to linear equivariant matrix factorizations. And we have a concrete geometric picture in the on the A side of what the flows are and what the different paths are. So they're determined by saying which of the guys decouple, and then there are some symmetries and things like that. And we have to reproduce it from the B side. And I gave a prescription on how to construct the defects on the B side. So basically it was some truncation of the identities of the gauge linear sigma model. So for each truncation, there's some different defect. And one can see that precisely these truncations, so the truncations, of course, have something to do with the charges that appear, and therefore they have something to do with which branes couples how to the defect, and therefore the which elementary branes get projected out is precisely matched by these truncations. And in particular, we have constructed using the gauge linear sigma model one different defects between different Landau-Ginzburg phases, and so in the explicit example that we indeed got all flow defects that exist between the two phases. Okay, so then my time is up and I conclude. So I try to give a construction of functors between brane categories in different phases of the GLSM. So we discussed various different phases and how to relate them by defects. And I also discussed defects that map a phase and to the gauge linear sigma model, and projectors that realize the branes of a phase as part of the gauge linear sigma model. Then my construction relied heavily on the rigidity of supersymmetry and of defect constructions in such theories. My concrete construction involved a choice of certain cutoffs, and in examples we see that these choices of cutoffs exactly present the choices of perturbation in the physical model or paths in the physical model. Yeah, here I write applicable to anomalous and non-anomalous examples. So we can look at moduli spaces, and we can also look at relevant flows. Yeah, so there are different classes of examples that in physical context tend to pose some problems. And it's in agreement with results that are obtained by other methods. So for example, in the physics literature, there's a program initiated by Herbst, Hori, and Page, where the same problem, like how do the branes map from one phase to another in a gauge linear sigma model, was addressed by using analytic properties of heavy sphere partition functions and heavily relying on things that happened in the gauge sector, whereas in my arguments, this gauge sector was decoupled and only played a role via equivariance conditions. Okay. Thanks, let me stop here.